I'm Adi. I'm with Adobe, and I'm really thrilled and excited to share our experience in running, actually migrating and running Kafka to Kubernetes across multiple clouds here at Adobe. Melissa mentioned that currently there's a majority of people, 90% of our users agrees that Kubernetes can host stateful services. That was not definitely the case 3 years ago when we started this journey. And I think the ratio, I didn't have the hard data, but I don't have the hard data, but I guess it was only 5 or 10% of users agreeing that Kafka stateful services can run on Kubernetes. But we took that hedge, and we are really thrilled that we made the right decision back in the days to select Kubernetes as an underlying runtime for our Kafka stateful service. A bit of background about myself. I'm with Adobe for 10 years. Right now, I'm a principal scientist with the Adobe Experience Platform group, and I led various big data teams throughout my career here. Back in the days, I ran Hadoop, HBase, and more recently Kafka. Why I'm here is that the reason I'm here is that I was one of the lead architects of this transition of our Kafka infrastructure to Kubernetes. And today I'm really going to share a couple of points with the community here. First of all, I'm starting with a bit of business context where we are operating here, Kafka at Adobe. Then I'm going to share a bit of the thinking when we started this process of migrating our previous Kafka infrastructure to Kubernetes, so the guiding principles. Then a bit of the Kafka operator, the Banzai Cloud Kafka operator we are using to drive all these deployments. Then the lesson learned, right? And there is one particular principle, this mechanical sympathy I'm going to share with you. Let's get into the main content. Adobe Experience Platform is the business we are running here at Adobe. It's really the flagship product in our digital marketing group, offering our customers a way to ingest, collect the data into our platform, and then derive value out of it using capabilities like personalization or optimize the journey, orchestration, campaigns, and all the marketing capabilities the customer are looking for. Behind the scenes, Kafka is really playing an important role, right? Is the core infrastructure allowing this data to be ingested and be traveling across the globe. We are running 14 regions, right, throughout the whole map. And as I mentioned, we are in 3 clouds, right? We have our private cloud, Amazon, and Azure, and in total we are running 25 production cluster, Kafka production cluster. The scale is, I would say, is really big in terms of Kafka today. More than 300 billion events accumulated per day, close to 1 petabyte of traffic in and out, and close to 2 terabytes of data stored at any point in time. Now, we've been running Kafka for quite some time at Adobe, right? So it's probably 10 years now. But when we started this migration, to Kubernetes, we really looked at the Kubernetes as the equalizer in terms of infrastructure, right? So we really want something that can allow us to run uniformly the deployment of our Kafka across different clouds. Different clouds being a must, right? Was not a nice to have for us, was really a must because this is our hosting strategy here. And we tried to lay out some principles, right? Some architecture principle. We wanted an infrastructure which is elastic, flexible, and scalable, while still remaining cost effective. Then, of course, operationally want to be resilient and disaster recovery ready, and have all the tenets of a good run system, having all the monitoring and alerting as a code, and the deployment and all the operation driven in a GitOps manner. Now, looking at these guiding principles and requirements, if you want, Kubernetes really fit the bill here and was no-brainer for us even back in the day to select as a runtime. Now, because we wanted to really be full in and be future-proof, right? We tried to select the best methodology and framework to run this service. And at that time, the operator framework was already a thing, so we selected that. But looking, and by the way, this is something that can apply to any operator, and it's part of the operator capabilities shared by the operator framework. We try to compare various operators across the different levels of maturity, right? And Kafka Operator, the Koperator, which is maintained by Banzai Cloud, now Cisco folks, really was for us the one that fit all the requirements. So we opted for that operator. There are other well-maintained operators like Confluent or Streamz. By all means, you should look at all those. For us, the Koperator was the chosen solution for our infrastructure, and we meanwhile also became active contributors to that code base. This is really the high level. I'm not going to insist. It's something that you can check, but it's really an operator using Prometheus and CruiseControl, which are already something that is being used in the Kafka community to drive all the Kafka operator. Maybe it's worth mentioning that among all the operators, Koperator is the only one that stayed out of stateful set. When you look at the stateful service, the stateful workloads, you may see a couple of, a bunch of operators making use of stateful sets in Kubernetes. While this is awesome because you are using something high level, it's also posed some challenges when operating or trying to fine-grain operate complex systems like Kafka. In this case, Koperator opted to manage individual pods, where each Kafka blocker can be surgically managed in case of any operation. So that's really, in the end, I think a powerful capability. Now, in terms of deployment, how we deployed this, we have multiple. We have the operator, of course, deployed in a management namespace, and it can operate multiple Kafka deployments. So the right-hand side deployment namespace can be replicated and watched by a single operator. Of course, that's a nice capability any operator has in Kubernetes. And bottom side, we have the monitoring namespace, which is delivering the observability capability for this. Now, that's kind of sums up how we got here. What was the thinking around selecting the right operators. And now I'm going to share the lesson learned while doing this, right? And you probably know this famous quote from Jackie Stewart, which was a former racing driver, which said that you don't have to be an engineer to be a racing driver, but you need to have mechanical sympathy. And I think this translates very well into our engineering space, right? You don't necessarily, to be a Kubernetes administrator to run Kafka, but you need to have mechanical sympathy, meaning that you need to understand how the underlying platform Kubernetes works in order to exploit it to its maximum capabilities. So that's what we tried to enforce throughout this whole journey. And what we learned, right? So when running stateful services, of course, you need persistent volume, right? So that was kind of the basic research we look at, and of course you have this across multiple clouds. In our case, we are using EPS, Azure Disk, and vSphere in our private clouds. But that doesn't mean that just selecting any PVC storage class is the right thing to do. So we had to look at the right configuration for each individual persistent volume, right? So, for example, in Amazon, in order to avoid burst I/O, you need to go above a certain disk capacity. In this case, 300 gigabytes, to have guaranteed IOs. The other quirk we learned is that volume binding mode is better if you select wait for first consumer, meaning that when you attach PVC like that, it will delay the binding of the disk to node until the pod is actually scheduled. So that gives a much faster start time for our Kafka pods in our case. What else? Kafka already has the notion of racks. So we map it to availability zones, right? So Kubernetes already has this nodes zone exposure, so we just had it to configure it via a node selector. Pod anti-affinity, right? As you know, Kubernetes is doing a great job in isolating CPU and memory, but not necessarily the I/O, right? I/O isolation is still something being worked on in Kubernetes. When it comes to stateful services, we opted for pod anti-affinity as a way to implement this, because in this way we can avoid multiple Kafka brokers, contending or sitting on the same underlying node. The other technique you can use is to have dedicated worker pools for these stateful services. Works well depending on your architecture. Request and limits, right? So we eventually set requests equal to limits just to have the pod placed into the guarantee scheduling class, which gives you a more priority compared to burstable and best effort scheduling class. Of course, at the pod level, pre-stop and shutdown hooks, right, are very important. Because it gives you a way to cleanly drain the pod, or in our case, Kafka broker at the end, right? For various stateful services, draining or shutting down clean is very important. So that's what the shutdown hooks and termination grace period can be used in Kubernetes. Kafka is really hungry when it comes to page cache. So we need to account for that when provisioning the memory, right? So in our case, given the request budget we set, we allocate only 70% to Kafka JVM. The rest goes to the page cache. So that's very important when you count the whole need in terms of memory. Also, very important, you need to account for other pods on Kubernetes node that may potentially contend with in terms of I/O, right? So, as I said, Kubernetes is not yet considering the I/O capacity, and one of the techniques was to over-provision, right? So Kafka pod is over-provisioned in terms of resources, so it can take the whole node. That's really for extreme use cases where we really need total isolation. The slow disk may be an issue. The way we solved it was to, of course, instrument and monitor the core vitals of the disk, the latencies, and act on them when they occur. The other one, when it comes to Autoscaler, I know we have a nice talk about Autoscaling stateful set, but really quickly, in our case, we wanted to make sure that Autoscaler, right, will not scale in unless is required. In our case, we can label the Kafka pods with a label with a tag that says "Do not scale in unless really needed." There are other considerations depending on your platform. We are running in our own platform called Ethos, but the operator may contend with other operators trying to auto-tune or optimize the configured resources. So you need to be aware of other operators running in your cluster. Last and a very important item for stateful services is how the operator or how the workload is tolerant to the Kubernetes cluster maintenance. As you know, Kubernetes needs to be upgraded, can be done via resources update, but also via full cluster upgrades where the nodes are really drained to, for example, install a new version of Kubernetes, right? So stateful services really need to be tolerant and cognizant of these operations, right? So having readiness probes is very important, but also using pod disruption budget for us was the more elegant way of signaling the budget, right? The disruption budget between our workloads and the platform underneath, right? So we heavily use of this way of sharing the disruption budget with the platform. When it comes to data, right, data is precious, right? So there are various ways to ensure disaster recovery. In our case, we made use of the global deployment of our Kafka, right? So for us, the backup is really an off-cluster backup, right? Where the data is shared with or is replicated across multiple sites. And in case of disaster, we can recover from these remote sites. Last but not least, metrics, right? For us, being able to operate and optimize ultimately revolved around metrics. We have everything as code, from monitors, alerts, dashboards, and we get notified whenever something goes wrong across the entire infrastructure. And with that, thank you for listening.